Find minimum in rotated sorted array 2. Problem summary: given a rotated sorted array of integers that may contain duplicate values, find and return the minimum element in the array. The array was originally sorted in ascending order and then rotated an unknown number of times. The input is an array of integers. The output is a single integer, the minimum element found in the array. Solution summary. First, check if the input array is null or empty. If it is, throw an illegal argument exception. Initialize two pointers, start and end, to the beginning and end of the array. Enter a while loop that continues as long as the start pointer is less than the end pointer and the value at the start pointer is greater than or equal to the value at the end pointer. Calculate the middle index as average of start and end. If the value at the middle index is less than the value at the start index, it means the minimum element is in the left half of the array. So, set the end pointer to the middle index. If the value at the middle index is greater than the value at the end index, it means the minimum element is in the right half of the array. Set the start pointer to mid plus 1. If the value at the middle index is neither less than the start nor greater than the end, it means the values at the start, middle, and end indices are equal, indicating duplicates. In this case, increment the start pointer and decrement the end pointer. In scenarios where all elements are duplicates, the start and end pointers are moved one step at a time to narrow down the search range. The loop continues until the start pointer is no longer less than the end pointer, or the value at the start pointer is less than the value at the end pointer. Finally, return the value at the start pointer, which is the minimum element. Attention! Do while loop when there is more than one element and the array is unsorted unless all elements are of the same value. Else return the start element. Note, if the second half is unsorted, we can rule out the mid element, while if the first half is unsorted, we can't rule out the mid element. If we can't tell which half is unsorted, nums at start is greater than or equal to nums at end, while nums at mid is greater than or equal to nums at start and nums at mid is less than or equal to nums at end. The only chance is that they are all of the same value. As the length is at least 2, it's okay to move both start and end. If there are no duplicate elements, we only need to check if the first half is unsorted by checking if the value at the middle index is less than the value at the start index. If so, move end to mid, else move start to mid plus 1. Complexity. The time complexity is O of log n in the best case where there are no duplicates, but it can degrade to O of n in the worst case when there are many duplicates. The space complexity is O of 1, as it uses only a constant amount of extra space. Search in rotated sorted array 2. Problem summary: given a rotated sorted array of integers that may contain duplicate values and a target integer, determine if the target integer exists within the array. The input is the rotated sorted array and the target integer. The output is a Boolean value, true if the target exists and false otherwise. Solution summary. First, check if the input array is null or empty. If it is, return false. Initialize two pointers, start and end, to the beginning and end of the array, respectively. Enter a while loop that continues as long as the start pointer is less than or equal to the end pointer. Calculate the middle index as the average of start and end. If the value at the middle index is equal to the target, return true. If the value at the start index is less than the value at the middle index, or the value at the middle index is greater than the value at the end index, it means the left half of the array is sorted. If the value at the start index is less than or equal to the target, and the target is less than or equal to the value at the middle index, set the end pointer to mid minus 1. Otherwise, set the start pointer to mid plus 1. Else, if the value at the start index is greater than the value at the middle index, or the value at the middle index is less than the value at the end index, it means the right half of the array is sorted. If the value at the middle index is less than or equal to the target, and the target is less than or equal to the value at the end index, set the start pointer to mid plus 1. Otherwise, set the end pointer to mid minus 1. Else, if the values at the middle, start, and end indices are equal, increment the start pointer and decrement the end pointer. The loop continues until the start pointer is greater than the end pointer. Finally, return false if the target is not found. Attention! If there is no duplicate element, we only need to check if the first half is sorted by checking if the start element is smaller or equal to the mid element. However, with duplicates, any equal sign won't make sense, and we have to rely on smaller or larger than without equal signs. Complexity. The time complexity is O of log n in the best case, where there are no duplicates, but it can degrade to O of n in the worst case, when there are many duplicates. The space complexity is O of 1, as it uses only a constant amount of extra space. Maximum swap. You're given a number, and you're allowed to swap any two of its digits just once. Your goal is to find the maximum possible number you can get after that one swap. The input is an integer. The output is also an integer, the largest number that can be formed by swapping two digits at most once. Here's how the solution works. First, convert the number into a character array so that each digit can be accessed and swapped individually. Create an array called lastPosition of size 10 to keep track of the last occurrence index of each digit from 0 to 9. Iterate over the digits starting from index 1, because the comparison requires that the digit you want to swap with must appear after the current index. For each digit, update its position in the lastPosition array using its numeric value. Next, loop through the digits from left to right, but stop at the second last digit. For each digit, check if there exists a higher digit, starting from 9 down to 1, that appears later in the number. If such a digit exists and its position is greater than the current index, swap the two digits. Immediately return the newly formed number by converting the modified digit array back into an integer. If no beneficial swap is found throughout the loop, simply return the original number. Edge cases include when the number is already the maximum possible. In such cases, no swap is performed, and the original number is returned. Also, numbers with repeating digits are handled correctly by using the last seen position. Attention! The loop starts at index 1 since we are only interested in digits appearing after the current one. The loop to scan digits ends at the second last digit, because we need something to swap with. Complexity. Time complexity is O(n), where n is the number of digits in the input number. Space complexity is O first, since we're only using a fixed size array of 10 elements regardless of input size. Verifying an alien dictionary. Problem summary. You are given a list of words in an alien language, and a string that represents the order of characters in that language. Your task is to determine whether the list of words is sorted based on that alien order. Input, a string array of words, and a string representing character order. Output, a Boolean value, true if the words are sorted in the alien language, otherwise false. Solution summary. First, create an array to hold the position of each character in the alien alphabet. The array size is 26, corresponding to the 26 lowercase English letters. Loop through the given order string. For each character, store its index plus 1 in the array, where index is its position in the order. Here we do plus 1 so that we can use 0 to indicate this char never appeared before. If we tried to set for an index whose value is non-zero, we know there are duplicates in order. Now, compare each pair of adjacent words from the input list. For each pair of words, start comparing characters from the beginning. If the characters are the same, move to the next character until a mismatch is found or one word ends. When a mismatch is found, compare the positions of these mismatched characters using the character position array. If the character from the first word comes after the character from the second word in alien order, return false. If no mismatch is found but the first word is longer than the second word, return false. If all adjacent word pairs pass the check, return true at the end. Edge cases. A longer word that starts with a shorter word must come after it, otherwise it's invalid. The input order string must not have duplicate characters. Attention! The array char pos has size 26. It keeps the position of each letter from the alien order. While filling char pos, the code checks if a value is already present. If it is, that means a duplicate character was found in the order string. In that case, return false. Complexity. The time complexity is O(n) times m, where n is the number of words, and m is the average length of the words. The space complexity is constant first because the size of the character position array is fixed at 26. Alien dictionary. Problem summary: given a list of words sorted lexicographically according to an alien language, determine the order of the alphabet in that language. The input is an array of strings, and the output is a string representing the alien alphabet's order. If no valid order exists, return an empty string. Solution summary. First, check if the input array is null or empty. If so, return an empty string. Create two hash maps. One to store each character and its out neighbors, and the other to store each character and its in neighbor count. Populate the hash maps by iterating through each word and each character in the words. Compare adjacent words to determine the alphabetical order of characters. If the next word is a prefix of the current word, return an empty string. If a difference is found between two characters, add an out-neighbor relationship and increment the in-neighbor count. Create a queue to store characters with an in-neighbor count of 0. Add all characters with 0 in-neighbors to the queue. Create a string buffer to store the alien order. While the queue is not empty, pull a character from the queue, append it to the string buffer, and decrement the in-neighbor count of its out-neighbors. If an out-neighbor's in-neighbor count becomes 0, add it to the queue. If the length of the string buffer is less than the size of the in-neighbor count map, return an empty string. Finally, return the string buffer as a string. Edge cases include handling null or empty input, detecting invalid orderings where a longer word is a prefix of a shorter word, and handling cases where a valid order cannot be determined due to cycles. Attention! The in-neighbor count should only be incremented if a new relationship is found. Adjacent duplicate words like z are not considered as prefix. Complexity. The time complexity is O of v plus e, where v is the number of unique characters and e is the number of relationships between characters. The space complexity is O of v, as it is determined by the space used by the hash maps and the queue, which store information about the unique characters. K closest points to origin. You are given a list of 2D points on a coordinate plane and a number k. Your goal is to return the k points that are closest to the origin. The closeness is determined using the standard Euclidean distance, calculated as the square root of x squared plus y squared. Input: a 2D integer array representing the list of points, and an integer k representing how many closest points to return. Output: a 2D integer array containing the k closest points to the origin. Edge cases to consider. First, check if k is less than 1. If so, throw an exception indicating k must be positive. If the input array has fewer points than k, return the array as is. Also, check with interviewer whether the output has to be sorted. Then you can decide whether to go to solution 1 or 2 depending on temporal complexity. Solution 1 is O log n. Solution 2 is O n on average, while may degrade O n squared in the worst case. Solution 1, we use a max heap to keep track of the k closest points seen so far. Create a max priority queue, also known as a max heap, that sorts points based on their squared distance from the origin in descending order. Note how the priority queue is initialized, new priority queue int array taking a lambda, that compares two int arrays a and b. When returning whether the distance of b is larger than that of a, points of longer distance are pulled first out the priority queue. Loop through each point in the array. Add the point to the priority queue. Each point is an array of length 2. If the size of the queue exceeds k, remove the point with the largest distance. This ensures that only the k closest points are kept in the heap at all times. After processing all points, extract the remaining points from the priority queue and store them in the result array. Finally, return the result. Complexity: the time complexity is O of n log k, where n is the number of points and k is the number of closest points to return. This is because we add and remove from the heap, which takes log k time. The space complexity is O of k, since at most k elements are stored in the heap. Solution 2. Use a variation of the quick select algorithm. Initialize start to 0 and end to the last index of the points array. While start is smaller than end, call a partitioning method that takes the points array, start, end. If the returned pivot index from the calling partitioning is exactly k-1, we know that the first k in the points array are closest. Else if the returned pivot index is smaller than k-1, move start to pivot index +1. Else move end to pivot index -1. The partitioning method takes the points array, start, end. In the partition method, choose the first point as the pivot. While start is smaller than end, do the following. While start is smaller than end and points at end are larger than pivot, decrement end. If start is still smaller than end, set start value with the end value and increment start. Then in the same loop, while start is smaller than end and point at start is smaller than pivot, increment start. If start is still smaller than end, set end value with the start value and decrement end. After exiting the loop, set pivot value to start position and return start position. Once the correct k points are at the beginning of the array, copy the first k elements into the result array. This can be achieved with system.array_copy. Return the result array. Complexity. Time complexity is O of n on average, due to the quick select algorithm, where n is the number of points. In the worst case, it can degrade to O of n squared. Space complexity is O of 1, since the operations are done in place without extra data structures. Median of two sorted arrays. You're given two sorted arrays. Your goal is to return the median of these two arrays as if they were merged into one sorted array. The input consists of two arrays, and the output is a single number, the median. Importantly, your solution needs to be efficient, with a time complexity of logarithmic order. The solution involves a methodical, step-by-step strategy. First, we calculate the total combined length of the two arrays and store half of it in a variable named k. If the total number of elements is odd, we call a helper method named findKTHHelper to find the k+1th smallest element. This is the median, and we return it as a double. If the total is even, we again use the helper method to find the kth and the k+1th smallest elements, then return their average. This average becomes our final median. The helper method called findKTHHelper is a recursive function. It takes 5 arguments. First array. Starting index in the first array. Second array. Starting index in the second array. The integer k representing the position of the desired element in the merged order. The base cases are as follows. If the start index of the first array has reached or exceeded its length, return the element at position second start plus k-1 from the second array. Similarly, if the second array is exhausted, return the kth element from the first array. If k equals 1, we return the smaller of the first elements of the two current subarrays. Otherwise, we calculate the midpoint positions in both arrays, first start plus k divided by 2 minus 1, and second start plus k divided by 2 minus 1. If the midpoint in the first array exceeds its length, we move the window forward in the second array by k divided by 2 and subtract that from k. As we have to use greater than half of k in the second array. If the midpoint in the second array exceeds its length, we shift the first array window similarly. If the value in the first array at its midpoint is greater than the second, we discard the first k divided by 2 elements from the second array and recurse. Otherwise, we discard those elements from the first array. This recursive pruning ensures that each step reduces the problem size roughly by half of k, keeping our time complexity efficient. Edge cases to consider. If one array is entirely consumed, the rest of the median must be pulled from the other array. If k equals 1, we return the smaller of the two starting elements. Attention! When k equals 1, removing k divided by 2 makes no sense. We directly return the smaller of the first elements. When a midpoint exceeds the length of its array, we move the search space in the other array, as we have to use more than half of k elements in the other array. Complexity. The space complexity is constant, O of 1, since we only use fixed additional space for recursive stack frames. Time complexity. The time complexity is O of log k because in each recursive call, k is reduced by half. Find median from data stream. Problem summary. The task is to design a data structure that supports adding numbers from a stream, and finding the median of all the numbers added so far. The input is a stream of integers. The output is the median of the numbers added at any given time. Solution summary. Two priority queues are used, first half and second half. The first half is a max heap, storing the smaller half of the numbers in descending order. The second half is a min heap, storing the larger half of the numbers in ascending order. When a new number is added, it is placed into either the first half or the second half, based on whether it is less than or equal to the peak of the first half. Note if first half is empty, directly offer into either second half or first half. This didn't matter, while be sure to check if first half is empty before peeking into it. To maintain the balance between the two halves, if first half has more than one element extra than second half, the largest element of first half is moved to second half. If second half has more elements than first half, the smallest element of second half is moved to first half. To find the median, if first half has more elements than second half, the peak of first half is returned as the median. Otherwise, the average of the peak of first half and the peak of second half is returned as the median. You may ask the interviewer if it's possible the getMedian method is called before inserting to handle the edge case of empty. Attention! Ensure the size of the first half is equal or one larger than the second half. Then the peak of the first half would be the median if the total size is odd, or the median would be the average of the peak of both queues when the size is even. Complexity. The time complexity for adding a number is logarithmic time due to the priority queue operations. The time complexity for finding the median is constant time, as it involves peeking at the top elements of the priority queues. The space complexity is linear, as it stores all the numbers in the priority queues. Explanation of optimizations. Follow-up 1. All integer numbers from the stream are in the range from 0 to 100. In this scenario, we can significantly optimize the solution by using a frequency array or a simple array acting as a histogram instead of heaps. Optimization. Create an integer array counts of size 101 to store the frequency of numbers from 0 to 100. Maintain a count variable to track the total number of elements added to the stream. Add num int num, increment the count at the index corresponding to the num in the counts array. Find median. Calculate the middle index by count over 2. Iterate through the counts array, keeping track of the cumulative count of elements encountered. To find the median. Odd count. The median is the number whose cumulative count surpasses mid. Even count. The median is the average of the two numbers whose cumulative counts encompass the mid-1 and mid indices. Time complexity. Add num O first. Find median O R, where R is the range of the numbers, in this case, 101. This is effectively O 1 since R is constant. Space complexity O R, which is O 1 due to the fixed range. Why this is better? This approach avoids the logarithmic time complexity of heap operations, providing constant time for add num and find median considering the range as constant. Follow-up 2. 99% of all integer numbers from the stream are in the range from 0 to 100. If most numbers are from 0 to 100, but a few outliers exist, a hybrid approach works best. Use a fixed array from 0 to 100 to store frequency of most numbers. Use a secondary data structure, like a tree map, for others.